Hello everyone, I am Kamal Utala, a pre-final year student in IIT Roorkee, and I am pursuing my BTech in Engineering Physics. Today I will be presenting on the topic Squids as magnetometers. As weird as it sounds, SQUID is an acronym for Superconducting Quantum Interference Device. So owing to its lengthy name, we will be referring to it as SQUID from now onwards throughout the slides. So let us jump into the contents of the presentation. Starting with Josephson effect. This is an important phenomena that we need to understand before diving into the working principles of SQUID. And then we will very briefly understand what is flux quantization in a superconducting loop. And once we are done with these, we will jump into the DC squared magnetometer, its working principles and its design. And lastly, very briefly, we will try to understand the applications of the DC squared magnetometer. So, starting with the Josephson effect. To understand Josephson effect, firstly we need to understand what is a Josephson junction. A typical Josephson junction is basically formed by two superconductors which are weakly linked by an insulator, or it can be a non-superconducting material, or even a different superconducting material from the given two superconductors works. But for the sake of simplicity, in the presentation we'll just consider that an insulator is placed in between two superconductors. So this is how a typical Josephson junction looks. Two superconductors and an insulator is sandwiched between them. We can rigorously find out the wave equation of this, but just by making an educated guess, we can guess that the equation of the wave equation of the Cooper pairs inside the superconductors will be something of the form in the equation 1, that is root ns into e to the power I phi, where ns is the density of the Cooper pairs in the superconductor and phi is the phase of the wave equation. So the idea is that in a Josephson junction, the phase of the superconductor 1 is different from the phase of the superconductor 2. So we will have like two equations which are phi 1 is equals to root ns e power I phi a, and we'll also have psi 2 is equals to root ns e power I psi phi b. Okay, so these will be the two different wave equations of the superconducting of the Cooper pairs in the superconducting material. Now if we consider the Schrodinger equation, you can see like this is the usual Schrodinger equation, like that is h psi is equals to e psi, but we can see that there is a extra term here which accounts for the coupling of the two superconductors. This coupling arises because of tunneling of Cooper pairs from one side of superconductor to the other side. So that is accounted by this term. K is the coupling constant. Now, if we apply a voltage V across the Josephson junction, we can very easily say that E1 minus E2 will be V times Q, where Q is the charge of proton. And then considering the reference point of energy as the midpoint of E1 and E2, we can modify the Schrodinger equation into something which looks like this. Now if we plug in the equation 1, that is these two equations that we got, into this equation and further do some simplifications, we get the Josephson equations. The Josephson equation basically describes the dynamics of the Cooper pairs in the Josephson junction. So as we can see, the first equation here describes the behavior of current with the phase difference of superconducting materials. We can see that there is a sinusoidal relation between the current and the phase difference. I0 is a constant value and it is based on the device parameters of the Josephson junction. We can also see that the second equation gives us the time evolution of the phase with a change in voltage. Interestingly, when we keep the voltage 0, so at 0 voltage we can see that d by dt of phi2 minus phi1 will be 0. This implies that the phase difference is constant when the voltage is 0. Now as the phase difference decides the current, even at a 0 voltage we can see that the Josephson junction has a current inside it. So this current is known as a supercurrent and this effect is known as Josephson effect. Like even at 0 voltage we are having a current inside the Josephson junction. Now coming to the VI characteristics of the Josephson junction, as we can see there is a dotted line between here. This represents normal ohmic behavior of a material. The normal ohmic behavior is V is equals to I times some R. But in a Josephson junction, we can see that in this region, the voltage drop is 0. Even though the current is increasing, we can see that there is no voltage drop across the junction. This basically suggests superconductivity. Superconductivity tells us that di by dV tends to infinity, or it's the same thing that dV by di, which is proportional to the resistivity of a material, is tending to 0. They both are the same thing. So as we can see, di by dV over here is infinity, that is dV by di is tending to 0 in this region. So this is the superconducting region. Superconducting region. So until the current value reaches the IC, the Cooper pairs inside the superconducting material doesn't dissociate. As soon as the current reaches this critical value, the energy of the electrons in the Cooper pair is enough for them to start dissociating. And as we know, Cooper pairs are a very important factor for a material to exhibit superconductivity. So after this point, slowly the Cooper pairs start to dissociate, and at some current which is greater than IC, we can see that the device starts to behave like a normal ohmic resistance. So this is the transition region from the superconducting to the normal ohmic behavior. As far as squids are considered, we will be operating near a point that is slightly greater than IC. We will shortly see why it is necessary, but for a rough understanding, we can see that to detect something we need to register a voltage. To make measurements we need to register a voltage, but as long as we are operating in the superconducting regime, we won't be able to register any voltage regardless of the current change. So we'll consider a place which is just above the IC value. So in this region the material will be still superconducting, although we'll be able to register a voltage too, but we have to make sure that we don't go a lot ahead the IC. We need to be very close to IC. Now let us look at flux quantization. What does flux quantization tells us? Consider a superconducting loop. So like basically there is a loop which is made up of superconducting material, and there is a magnetic field that goes outside the paper, outside the field of this view, that is this. So if a flux should exist between this, that is an integral multiple of phi naught. So n is an integer. N is an integer. So the flux values can only be phi naught, 0 phi naught, 2 phi naught, 3 phi naught, and so on. So any other value than this cannot be allowed inside this loop. So this is basically what flux quantization is. As we can see, phi naught can be calculated using Planck's constant and the charge of proton. We can also see that the phi naught value is very less, and it is in the order of 10 to the power of minus 15 Webers, which is a very small value. Now let us look at the working principle of a DC squid. To understand the DC squid, consider two Josephson junctions connected in parallel. This symbol here denotes the Josephson junction, a straight line with a cross on it. So we can see that there are two Josephson junctions which are connected in parallel. Now suppose there is a magnetic field. A magnetic field is switched on and a flux of phi dash is being generated in this region. So we have a flux of phi dash that is being generated in this region. Consider a bias current which goes through this. This is a current that we are applying. So as both are identical, the current will split into two. Now comes the interesting part. We know that by flux quantization, phi dash can take values which are an integral multiple of phi naught. So consider a case where phi dash is between phi naught by 2 and 0. So in this case, it's not an integral multiple of phi naught. So what the superconducting loop will do is, it will produce a screening current. A screening current will be produced which will reduce the net flux of the conducting loop to 0. So basically, because of IS, another magnetic field will be induced which will cancel out the flux that is created by this external magnetic field. So the energetically favorable decision is to make the flux quantized, that is making it 0 into phi naught. So basically the IS is generated to make the flux integer. So now as IS is additionally added to the loop, we can see that it will subtract from the upper part and it will add up on the down part. Now this creates a problem. While the screening current was not present, the current going through this loop was just IB by 2. But now as an additional current of IS is also added, it might be possible that adding up of current could have increased the total current of I greater than the critical current of the Josephson junction. Basically, IS will add up to IB by 2 and it can become more than IC. So if a condition arises where IB by 2 plus IS is greater than IC, basically the bottom part of the circuit will become a normal ohmic resistance. So it won't be superconducting anymore. And similarly, as the bottom part is not superconducting anymore, the whole current will be going from the upper part, and this will lead to the consequence that the upper part will also become a resistor, because a large current is flowing from this part as this has become a resistor. So basically, once this condition is arrived, we can see that both of them become resistor. So So until the flux is being increased from 0 to phi naught by 2, a screening current in the counterclockwise direction is being generated, and that adds up and subtracts from both of the branches of the Josephson loop. But an interesting thing happens when the flux is increased and it goes from phi naught by 2 to phi naught. In this region, we can see that it is energetically more favorable for the flux to quantize towards phi naught. That is, a favorable current will be generated, which will add up to the external flux generated by B. That is, if the flux is something greater than phi naught by 2, a screening current will be generated, which will add an additional flux to this, and they both will add up to phi naught. So basically, the direction of the current will be reversed, which will favor the flux and it will add up the flux in it. So in this case, what happens? The bottom part is the current in the bottom part is subtracted, and the top part is added up. It is again the same case as the above because of the symmetry. We can see that it is the same case, that but just the branches are interchanged. So until a flux of phi naught by 2 is made by this IS current, the current will be in this direction. As soon as the flux generated by IS increases more than phi naught by 2, the direction of the current changes. Basically, the agenda of the IS is to quantize the flux. It will either make it phi naught or it will either make it phi, depending on which one is easier to do. In the first case, it will try to make it 0. Sorry, this is not phi, this is 0. This is 0. So in the first case, it is easier for the flux to go to 0, and in the second case, it is easier for the flux to go to phi naught. So that is how this will work. So coming to the characteristics, we can see, let us first fix the bias current in which we will be operating, and this is the normal IC of the Josephson Junction. Now, as we can see, when the flux is increased, as the flux is increased, the IC of the material is decreasing because there is an addition of current in the loop. So the amount of current that we can send is basically less. So what happens is, the critical current which we can apply will reduce. It will be IC dash, which is lesser than the normal IC that we know. So as IB is fixed, so basically the current is fixed, we can see that there is a voltage change over here. So as we change the phi, the current, the voltage value will oscillate from this point to this point depending on phi. I hope that's clear. So as we can see, as we are increasing the flux, first the current increases until it reaches 0.5, that is phi naught by 2. At this point, the direction of the current reverses, and then it again starts to increase. And at certain point, that is 1, which represents phi naught, at this point the screening current is 0, because the flux is perfectly an integer, so we don't need a screening current. So as we can see, as this flux is changed, the voltage also oscillates. This is the delta V value that we got from here. So basically the voltage is oscillated in this region, which is represented in this graph. As we change the phi, we can see that the voltage also changes. So basically what we have created is a flux to voltage transducer. So we can see that the units here are in the units of phi naught. Phi naught is in the order of 10 power minus 15. So basically we are able to convert changes of magnetic fields or magnetic flux of the order 10 power minus 15 into readable voltage values. So we are able to create a very sensitive magnetometer which can detect flux that are of the order of 10 power minus 15. So summing up everything, what happens is as we change the magnetic field, an IS is developed, the screening current is developed, and because of the screening current, the critical current which we can send into the Josephson loop decreases. That is, for n phi naught, the IC will be the maximum IC, which is the normal Josephson junction. As we increase the phi naught, we can see that the IC will be decreasing, and at n plus half of phi naught, we will have the minimum IC, that is IC minimum. So at a constant bias current, by changing the phi value at a constant IB, we can basically vary the voltage, and the voltage will vary between these two parts because the current, the VI characteristics will be changing with the change in phi, and we get a equation between delta V and phi. So basically we create a flux to voltage transducer which is very sensitive because it can do measurements of the order of 10 power minus 15 Webers. Now consider the design of this DC squid. So we can see that there is a squid over here, and these are detection coils. These detection coils are basically to pick up the magnetic field of the sample. Consider a sample is placed near the detection coil. The detection coil will pick up the magnetic field of the sample, and this magnetic field will be then sent to the squid, like coupled with the squid device, and then the squid device will have its own calibration. So basically we'll have the change in flux, and that will be converted into a voltage reading. So the voltage reading, so a flux reading will be changed into a voltage reading here, and then accordingly we will find out the magnetic field which is being produced by this sample, and this magnetic field can be as low as 10 power minus 15 Webers in the flux. Some of the interesting applications of this can be like detection of geological formation in the earth, like if there are some changes in the earth's geology, then corresponding magnetic field changes can be observed. As Earth's magnetic field is very weak, the changes will produce a very weak magnetic flux change, but that can be picked up by our squid magnetometers. It is a device that really doesn't need contact with the sample. We can use it for a non-destructive testing of defects in any sample. So if there is some defect and it is changing the magnetic field over there, we can pick it up using the DC squid magnetometers. And then there is magnetoencephalography. In encephalography, we basically try to study the head and the brain parts, and there are very weak magnetic fields near the brain, so they can be mapped using a DC squid. And also, we can detect very weak magnetic fields which are produced by the birth of stars or some cosmological event, and we can study the evolution of our universe. Well, this was just an introduction to squid. Like squids are these are like a new and an emerging technology, that is quantum technology. So these are very new like not very new but comparatively new sensors, and a lot of development needs to be made in this. I tried my best to I tried my best to explain the topic. I hope you all liked this video.